this one on. Somebody guys took the derivative. What'd you get?
Negative a times 2 pi b times 2 pi b.
Because it's all in terms of t, so the rest of it's just a constant. It would be a lot nicer if the 2 was in front of the a. I apologize. But as we go on, and as we do as double prime, and as we do as triple prime, what they're asking is what would change if you doubled b. So if you plugged in 2b instead. And right now in this one, if I plugged in 2b, what's going to change?
The outside's going to become 2.
The velocity is going to, instead of having a 2, it's going to have a 4, so it's going to be doubled, right? Now, yes, it's going to change in here too with the sign argument, but that's not going to change the amplitude. That's not going to change the overall coefficient. This is going to change the overall coefficient to make it 4. Now, when I take the derivative again, aren't I going to have, the a is still there, but now I have another 2b that's coming out? So now I'm going to have a 4a pi squared b squared with my sign. So what's going to happen when I plug in a 2b here? So it's going to be, the velocity is going to be doubled when you plug in a 2b. The acceleration is going to be quadrupled because it's going to be 2b squared, which will be 4b squared. So now you have another 4, so it's 4 times greater. And then what's going to happen, can you guys guess when you come out for a jerk?
8 times.
Yeah, it's going to be now cubed. You're going to plug in a 2b. 2 cubed is 8. It's going to be 8 times greater. So what they were having you see is what happens if you plug in double the, what was it? Frequency? Frequency.
Whatever.
If you double the frequency, how is it going to affect its velocity, acceleration, and jerk? So you just had to figure out when you took those derivatives and you plugged in, how is that power of b going to affect the overall coefficient? Does that kind of make sense? Okay, ask on 61. Number 65. Was there anything else from section 4.1 or was that it? I'm going to go peek at 65 and the answer key.
Not for you.
I mean, that one should be right.
No, take home for it.
I think it's right too. I just
they just rewrote it as a simplification, put the 1 over s squared on the side.
I just understand why people had a question on it, because just getting s squared. Ooh, no, they did something different. Are they doing it with respect to t? What's my 65?
It's a noise that I make when I do something.
That's so cool. Tell me more.
Pause. Kiddos, hold on. I should not be the only one studying this right now. It's different than what we did on the board. Pause. Focus. Because if you guys understood what I did on the board, guess what? It's all wrong.
Aww.
And here's why. They did not specifically talk about time, but I guess they just wanted us to assume that velocity was in terms of time, which was Noah's question earlier. So we assumed it was dds, but instead it should have been dt. At which point we would have v prime times s prime. So we should take the derivative of this with respect to time. The dilemma is that's going to be a bit messier, because we would take our derivative that we have, our negative k over 2 square root of s cubed, but we also need to do times ds dt.
Mm-hmm.
I think they were a little too complicated for this one.
I agree, but they were able to get out velocity. I'm trying to figure out how.
I think because they never put in
Because dvds, that's what we found. ds dt would have been just something that we'd have to write because we don't have ds dt. So then they went ahead, oh, ds dt is velocity. Oh, that's how we got rid of it. Because then velocity over velocity cancels. So because we didn't multiply by ds dt, that's how we got messed up. I lost that marker.
That's too complicated.
So it should have been v of t. That was my problem. In terms of position. So then acceleration would be the derivative, but the derivative would need, end of the day, ds dt. Or s prime. And what's ds dt, or the derivative of position, the same thing as? Just velocity itself. And then my velocities would cancel. So we forgot to enroll. Huh, ironic, isn't that kind of what we're supposed to be doing? I didn't think of it in terms of time though, because they didn't specifically show it. Struggle. Okay, so if we had done S prime, that would cancel out the velocities, then it would be a much easier or clearer.
Yeah, no.
And then they end up having the same thing as we did. Negative k squared over 2 is our constant, and then s squared is the denominator. Struggle. Okay, section 4.2. Did you guys have anything remaining from that one?
55.
Oh, I just closed it. Struggle.
55.
Okay, I just heard 55 from multiple people. Anything else beyond 55?
56.
56? We don't like those. All right.
62.
$55 is at the bottom, right? Alright, so then we have the Folium of Descartes. They have a picture, but it's not on this page. You guys have to go back and look at a different page to find it. But they're asking us to find the slope, which is dy dx, right? At the points 4, 2, and 2, 4. All you have to worry about for A is just implicit differentiation, true?
Yes.
Where did we get stuck? C? Okay, so then what did you guys get for dy dx for letter A? Because in letter C it talks about vertical tangents, so I need to think about tangent lines, hence dy dx.
3-1.
3-1. I mean the equation.
3 y minus x squared over y squared minus 3x. That could be wrong.
Okay, double check.
Actually, 0.5.
Question, what does it take to have a vertical tangent?
When the bottom
When the bottom equals 0. Horizontal tangent is when the top equals 0. So when the bottom equals 0, remember, find the coordinates of point A. So if we just set y squared minus 3x equals 0, we could say, already not actually put it equals 0. If they were asking us for an equation or expression or a relationship, we could stop there, but they're actually asking us for a point. Figure, oh, is 4.7 on a different page?
Yes.
Yes.
My thing was there was like a word A.
It goes.
There's no point A at all?
I didn't see it.
There's a point A. There's a point A.
Yeah, there was.
It's right. It's on the right side of the little loop.
What page was it on? 164?
So I don't know.
It's on the first page of 4.2. Page 116, 4.2. I got you. Yeah. What is it?
Down right there.
Oh, he's right there.
Oh.
So I'm trying to find something in the first quadrant that has this slope of 0, so the x is... Alright, so the relationship of y squared minus 3x, that's x equals... y squared over 3. Well, I just rearranged. I took the denominator equal to 0, rearranged for x, because that's the easiest way. And I need an x point.
Would it be negative? Never mind. Would it be negative?
And there was no other clue.
I mean, I just plugged in points that would make it 0, 0 on the bottom. Like,
You could, like, I'm guessing that they want like a whole number, not like a partial, but
no, I plugged in the point like 1, 3 or whatever.
right, like 0, 0, 1, 1, 1, 2, 1, 3, and then 1, 3, found it.
Yeah.
And then you could do 3, 9.
You could also do 3, 3. Oh,
No, 3, 3 would. Oh, yeah, you could do 3, 3. That's awkward though. But just the testing? They give us those every now and then, but they're not super fun. What number was that?
everyone's going to do it. They just don't
55.
try.
Shoot the shot.
I didn't notice the sign.
We didn't look at A or B.
Yeah.
I quote B and C.
She's
She's on. Yeah, how do you not like this? That's because you can't. Maybe so loud.
You're good.
I think you have to. You should take a stand in color. Did you
Yeah, without any extra qualifications, kiddos, I think that we could just literally
Teacher has that.
do what we've done in other AP problems where we plug in nice points. 0, 0, 1, 1, 2, 2, 3, 3. Not ideal. There isn't a way of actually solving it. It's more of a testing problem. Because they didn't give us, I was thinking that they might have given us extra information here. They did give us the graph, so we did know that X and Y both needed to be positive, because it was in the first quadrant. And at which point we just have to think about when will 3x equal y squared, when will the square of something equal 3 times? Well, 3 times 3 would be 3 squared, so.
4 squared root 12.
Right, but then you start going into decimals, that's why I assumed it was like an AP question where they wanted the nice answer.
Square root calculus, since you're using extra square in the wall. Anything's possible.
It's possible.
True, but you need the square root squared to cancel out with the 3x. But yeah, you could make the x and make the y, you're right, there could be multiple points. That was interesting. I didn't like that problem very much. I like the idea of setting the denominator equal to 0, which is why I chose it. I just didn't realize that you guys had to do the experimentation of just putting in solving. That was messy. 56 was another one, right? Oh, that one's a little bit easier. What do you guys do for 56? Good. And then you had to find the slope at 1, 1, right? What did you get for the slope?
Negative 1.
I got one.
No, wait, well, the normal line is.
But then for the normal one, it changes.
Oh, so it was 1 and then the opposite reciprocal for normal? Is that what you mean? Negative 1? Okay, now we're trying to figure out that it intersects the curve at what other point?
Yes.
Yes.
Mm-hmm.
And so then you plug it into the formula, the point slope formula. Only using 1, 1, right?
Well.
Yeah, you can make the equation of the line. That would have been, yeah, that would have been the point. So you have y equals negative,
X plus x. X plus 2.
you have x minus 1. I'm just solving it. And you have y minus 1, so then plus 1. So plus 1 plus 1. Yeah, x plus 2.
Negative x.
Thank you.
Very good.
Then can't you just plug it in for the y values and then solve for x?
Yes.
Because you need to take, remember, whenever they say something about the original curve, you have to go back to the original curve. So now that you know y equals negative x plus 2, plug it in, and solve. What did you guys get for x?
3.
Just 3?
3, yeah.
Okay.
Negative 1.
Yeah, 1 was already one of the points. That's why they said, oh, I remember checking this one. They said just count the point 3. And then, but pause, point, you need an x and a y. So you'd have to plug in then to solve for y. Would have been quadratic. Was there only one y value or 2?
3. 2.
Could have only been 2.
1.
Because 3 squared is 9. And then you have 6y, then you have minus 3y squared. Factor a 3 out of everyone. And we just would have had y minus 3 and y plus 1.
That doesn't come out to negative 3. That's positive 3.
Oh, that doesn't.
Yeah. You can't
I
get
put
wrong.
the x values into the line equation, the y equals negative x plus 2, and I got
Oh, because you solved that one too. That's a good one. Negative 3 plus 2 would be negative 1. Did I plug in wrong? I might have. 3 squared is 9. Oh, I didn't subtract the 9. Sorry. I subtracted it all to the other side, but not the 9. That went to negative for my first term. I find that to be messy. Then you would have had your y minus 3 and your y plus 1. But you're looking specifically for intersecting the curve.
Negative 1.
I would have said 2 points, right? Didn't you guys just say there was 1?
Well, I'm 1 and 3, yeah.
Well, but then that's negative.
Y equals 3 and negative 1, which means 3, 3, and 3, negative 1, right? It does say at what other point, at what single other point. Oh, then you test it in the line. That makes sense. Because the line has to actually hit that place too. So then if we go ahead and plug in 3, -1, only one of them should work. So -3 plus 2, sorry, the x. -3 plus 2 is just the positive. Sorry, the -1 option. So Lucy's way of plugging into the line was probably the simplest way of figuring out the 1. If you had plugged into the original curve, the curve does go through x equals 3 2 different times, but the line only hits at the point 3, -1. So yeah, plugging into the line is probably the fastest way, or the easiest way. I also heard one that had to do with the 60-something. What was the 60-something? 62?
That's
Multiple choice one, right?
Thank you. I appreciate that.
What do you guys think is your first derivative, just to help check?
Oh, very big number.
Oh,
Oh, so we just pull up the answer. We just pull up the answer.
it's -2x plus y over -x plus y.
The answer's A.
You get the answer?
Yeah, so we want to know how to get
61.
It's just,
62.
this one you just have to.
62 is that?
Yeah, those
Yeah, that's what I wrote.
Oh.
Okay, so the original derivative was y minus 2x over 2y minus x as you did your initial, what, quotient rule?
Yeah.
Then you had to do bottom d top, which is, they're writing kind of messily. They're doing y primes. But bottom d top minus top d bottom. Then the name of the game was you had to plug in your, well, it's up to you. You could have simplified first. They went ahead and FOILed first. Then they started collecting their y primes, trying to simplify. They were able to actually like cancel out some like terms and stuff first. So then they were able to get to this simpler expression. It is kind of small. A simpler expression where they were then able to plug in dy dx. If you had plugged in dy dx earlier, you would have been okay. It just would have been messy. So it might have been something where before plugging in the dy dx, simplify first, see if any of those extra y primes cancel, and then plug in a much simpler way, and then just simplify the complex fraction. And you're done. But yeah, if you guys had plugged in dy dx right away, you would have had quite a bit of complex fractions to simplify. Quite a bit of simplifying. Yeah.
If we get like a similar problem on like the AP multiple choice question, and then we are time restrained, you recommend us skipping that one and just like guess the answer?
Yeah, maybe skipping that one. Or, I mean, I would probably come back to what I would say here. If you see y primes in multiple places, just try to simplify it as quickly as possible before plugging in. That will shorten the problem if you have a little bit of time. But otherwise, any second derivative is going to be long and implicit. So if you had to choose between that and another one, I would choose the other one probably. If that was your question. Okay. Anything else remaining, cool kids? All right. Let's go ahead and get into notes. We were going to do some practice, but let's just go straight. I have like a long answering one that we might try tomorrow, but I think your homework questions pretty much went over all the things I was going to have you practice in your workspace. So, derivatives of inverse trig. What you have up there is pre-cal stuff from inverse trig.
I'm excited.
Took us quite a few days of pre-cal to get through all of that. I just went ahead and sketched the graphs really quickly. Remember when we're talking about inverse trig, technically it is restricted when we solve the inverse functions, not when they give us something like when is sine 1/2. We have to think about all the different places that happens in the unit circle, coterminal. But if they do give us an arc sine, cosine, tangent, which they can do, or inverse, we do have to at least be somewhat prepared for the domain restrictions that we need to consider. You guys know that inverse trig is the same thing as the original function with the x and y switched. Sometimes it's easier to deal with it before it's moved around, before the inverse is brought in, which is why I show that notation. But you do switch the x and y tangent. 5 or 6 for A?
Go.
Need the third or fourth quadrant. Fourth quadrant. but not going positively, going negatively to the fourth quadrant. Oh, I didn't know you were asking me. I don't know, to be honest. Probably Melinda Grace. At one point it was Mackenzie Grace. I found it in the book already. Probably Kenzie. So who's Melinda Grace from?
Guy Mackenzie.
Yeah, no, I don't think, I think it was Mackenzie's guy.
You put it in
Is it, would you say it's harder? Like, I find for teachers it would be a lot harder to name. Like,
Anybody that works with kids.
because it's like, oh, I like to name Noah, but there was that one kid, Noah, he was horrible.
No, I've had lots of friends that are teachers and have had kids and they, like their spouse has really wanted one name and they're like, no, I can't.
Oh.
Because it's
My
happened a lot.
aunt and uncle, they're both teachers, so when they have their son, they're like, what are we naming?
Like, what's the name we have? We just gotta create the weirdest one possible.
Are you guys got the restrictions?
Almost. 6 letters whenever it comes up. That's when you name our children.
Let's pick a thing.
Arc side of -1/2, what do you guys got?
Negative pi is 3.
Negative pi over?
3, 6, 4. One of those.
Negative pi over 2, pi over 2s have zeros or ones.
No.
Pi over 3.
Oh, I apologize, yes, negative pi over 2 to pi over 2, 0 to pi, and negative pi over 2.
Pi over 3. Whatever. Pi over 6 then.
Wait, oh, I'm dumb.
I had a 50-50 chance.
Sine is 1/2 at 30-degree angles. Remember, sine is
I will
opposite.
fight you
Struggle.
anytime.
Okay, calm down. Corey, put your phone down. How about cosine of 0? Wait, pause. Could I have put 11 pi over 6?
Yeah.
Yes.
Except, is it in the restriction?
No.
Okay, so if I'm actually solving an inverse trig function, I would need to put negative pi over 6, right? How about cosine, arc cosine, I apologize, of 0?
Undefined.
You're thinking 1 over cosine, I don't want that. I want arc cosine of 0. When is cosine equal to 0? Gabby got it.
Negative pi over 2.
Not. Well, negative pi over 2 is true,
Yeah.
except restrictions. I only wanted between 0 and pi.
Oh.
So remember, I even have the quadrants. Sine, inverse, I'm looking at first quadrant, up 90, fourth quadrant, down 90, up pi over 2, negative pi over 2. Cosine, I'm looking at quadrants 1 and 2 for the principal values, so 0 to 90, 0 to 180.
How are you getting these?
Math.
Wait, pause. Where am I getting these as in the restrictions, or where am I getting these as in the answers?
The answers.
I remember I'm asking myself the question, when does sine equal -1/2 between negative pi over 2 and pi over 2? And sine equals -1/2 in the fourth quadrant at -30 or negative pi over 6. Our cosine, when does cosine equal to 0? Cosine equals 0 at pi over 2, 3 pi over 2, but I just want the principal one, and that's going to happen at pi over 2. Last but not least, when does tangent equal √3?
Pi over 3.
If it helps, for just a few of you, remember it's going to be sine over cosine. So sine must be √3 over 2, and cosine must be 1/2 in order to equal √3, right? And that's going to happen when opposite is taller, which is going to happen at a pi over 3 or a 60-degree. So it's reminding you of inverse. Inverse is going backwards. Inverse is going from a value to an angle. Does that make sense? Reminder. And what'd you say, Noah? Mm-hmm. Katrina.
So where you're writing the grade on the graphs, is that where it can be?
Yeah, because remember inverse, well, it's been a long time. The inverse functions, they need to pass the original needs to pass the horizontal line test. I can't have it repeating, because if it repeats, then one math problem has more than one answer.
Okay, but then how is that 1 and 4 not even touching the like,
Oh, pause. Quadrant 1 and 4 means the angles in quadrant 1, 0 to 90, and the angles in quadrant 4, negative 90.
Isn't it quadrant 3?
No. I'm not talking about the quadrants that the graph is in, I'm talking about the quadrants of the unit circle.
Oh.
I apologize.
Okay.
So this would be negative 90 to 90, or negative pi over 2 to pi over 2, which in the unit circle would be quadrant 4 and quadrant 1.
Okay.
Does that make sense?
Yeah.
Yeah, it was just like my little way of pointing you back to the unit circle, thinking of where to look for those answers.
And tangent is not equal to just
Not equal to, because vertical asymptotes at negative pi over 2 and pi over 2.
Okay, cool. Thank you.
Okay, so, pause, we already did this, right? You guys already have the arctangent graph in your forever card?
Forever number 1.
Yeah.
Okay, good. For some reason I didn't get it this year, I don't know why I missed it, but you guys already know the graph of arctangent. Looks like the cubed root of x, except it has the vertical asymptotes at negative pi over 2 and pi over 2. So you guys don't need to add that, it's already in there. Let's keep going. Last year they didn't have it, huh? Well, I apologize. Tangents, vertical asymptotes become arctangents. You're right, horizontal asymptotes. Good. Okay, so inverse function derivatives. Woohoo, remember this one?
This stuff is fun.
Inverse function derivatives. We're going to actually kind of talk about it a little bit different way than last year, not a bad way. I think I even kind of used it to try to help you guys last year. If we know the point f inverse of a equals b, if we know the point f inverse of a equals b, then we can say the derivative of f inverse at a is 1 over f prime of b. We did also talk about last year something to the effect of if g is the inverse and f is the original. We're trying to find g prime. We could say it'd be 1 over the original prime, 1 over f prime of g of x. It just gets confusing because the x's of the original are the y's of the inverse, and the x's of the inverse are the y's of the original. So the other way of looking at this point, they could give you f inverse of a equals b, or they could give you a equals f of b. So here's the struggle. You could be given a point of the inverse, or you could be given a point of the original. And depending on which one they give you, you have to take different pieces to put in. For instance, if you're trying to find the inverse derivative at a, and they give you an inverse point, you're looking for the y of the inverse to plug into f prime. And if you're looking for f inverse prime of a and they give you an original point, you're actually looking for the x of the original to plug in. So either way, you're looking for the x of the original to plug in that maps to the x of the inverse. So looking down here at this one, find f inverse prime of negative 1/2 for f equals sine of x. They didn't give you any point. We have to kind of figure it out ourselves. How would we find this derivative?
Well, you have to take the derivative of x.
You have to take the derivative of f of x, good, and you do 1 over every inverse function. Taking a derivative, it's 1 over the derivative of the original. And who's the derivative, or what's the derivative of sine?
Cosine.
Cosine. The struggle is, what do we plug in?
You plug in the one negative one, the sine, then you have b, then you plug in b.
We need b. We need the x of the original, and this is not it.
Mhm.
So this is the A, this needs to be set equal to the original. So we're gonna take -1/2, set it equal to sign, and how do we find the sign value that goes along?
Sign inverse.
Sign inverse, and what didn't we just do that one?
Yes.
What's sign inverse of -pi over, sorry, of -1/2? If they don't give us any restrictions, we're gonna have to come up with it on our own. When we plug in -pi over 6, how do we finish the problem? Solve it. And what's cosine of -pi over 6?
2 over square root
Yeah, root square root, sorry, root 3 over 2, which it is 1 over, which means it would be.
2 square root 3 over.
Now question, have we ever solved any type of that problem a different way before?
No, not really.
Who's the inverse? Who's the inverse of sine?
One over
Arc sine.
sine.
So couldn't I have said G equals sine inverse of x? And I want you to find G prime of -1/2.
Mm-hmm.
How do we find the derivative of an inverse? Do we have to use, yeah. Don't we have a formula for the derivative of sine inverse?
Or x
Oh,
squared.
it is 1 minus u squared times.
That's right.
Now, u is, wait, who's inside of sine inverse? X.
X.
So what happens if we plug in -1/2?
Well,
-1/4.
1 over square root.
Positive 1/4. Oh, so close.
So square root.
3 times square root 3.
Wouldn't that be 1 over square root of 3 over 2 and then flip it? Yeah. So question, is there a way of solving inverse trig without the inverse trig formulas?
Yes.
But does the AP force your hand to do trig inverse derivatives this way?
No.
No. They allow you to memorize the shortcuts and get to it this way, right? But the problem is, what are you going to have to do in order to be able to do it this way? Have them memorized again. True. But could you technically solve it the inverse function way? Yes. And what does the AP sometimes force your hand to do? Solve inverse functions. They just don't usually apply it to trig. But I wanted to let you guys see, hey, we can solve inverse trig derivatives using the actual inverse way. Now, what's going on? What am I trying to show you through all of this? I'm having you review what it means to be one-to-one. I'm having you thinking about original functions and inverse functions and how the points flip on one and the other. Reflecting one function across the y equals x line and then thinking about the slope. This is all one great way of visualizing why the formula on the page before, why this process of to find the slope of the inverse, I have to do 1 over the slope of the original at B instead of at A. We did struggle with this a bit last year in the visualization, and maybe we'll come back to that if I feel like it's super important. But for right now, what was the title of this actual section, cool kids? It's inverse trig specifically. So the page before is great for visualizing on your graphing calculator why does this formula work the way it does with 1 over f prime of b. But our objective is truly inverse trig. So let's go ahead and review really quickly where those shortcut formulas come from. Is that okay? Okay. If we're having issues with inverses, we might come back to that visualization. But for right now, with inverse trig, let's just get to where all this comes from. If I'm trying to derive x equals sine inverse, y equals sine inverse of x, I can say it's the same thing as what I showed you earlier, x equals sine of y. And if x equals sine of y, that means for some angle y, the opposite over the hypotenuse is x over 1. True. If x equals sine of y, remember, take sine of both sides or switch the x and y and make it the non-inverse. If that's true, then I can say sine of some angle y is equal to opposite over hypotenuse x over 1. Now, if that's true, what would my adjacent side be?
Square root of one, it's 1 squared minus x squared.
So, my adjacent is c squared minus b squared. Pythagorean theorem. And if I was to ask you to take the derivative of this guy, d dx, what would you do? So doesn't dy dx equal 1 over cosine of 1? And look at your triangle, what is cosine of 1? What's adjacent? Square root of 1 minus x squared, and what's the hypotenuse?
1.
Is that the formula I had you memorize last year? Yeah, and that's where it comes from. And we kind of saw these last year, but in the moment you were probably still reeling from the whole idea of inverse trig and having to think about derivatives and the whole inverse function thing. So maybe it makes a little more sense now as to where these actually come from. The shortcuts literally just come from the triangular relationships between what we know about sine and what we know about differentiation and chain rule. So if that's how we get the derivative of sine inverse, could we use that for all the others? Could we use that idea for the function that we just found, for tangent inverse, and for all of them? And the answer is yes. Now I'm actually going to take this guy away because we already did him. I think I didn't do him last year, so I wrote him again. We might peek at tangent inverse, what to do with u prime and how that works. I'm pretty sure we didn't do that last year, but for right now, let's just end here. You guys might want to take a quick picture of it. Remember your inverse trig rules? Do you have them in your forever cards? Don't they make things a lot easier if you just have them down pat? I think so too. All of them are going to be negative when you have trig functions with. And don't forget your u prime. We'll see if your reports are good tomorrow with the calculation. Review inverse trig derivatives. Try 1, 4, 3. Let's see if you get stuck.
Yeah, you suck. I know you had time.
4, 3, do them.
I hate everybody in your classes. Yes.
Sounds good.
Yeah, that's almost I'll help you with that.